Hi everyone! Today let's talk about session 4.2, the vector space Rn and subspaces. So today we will get formal about what is a vector space, and we will generalize the results from R2, R3 to Rn. So Rn consists of all the n tuples of real numbers. So that is an ordered list of n real numbers. So here we have n coordinates. So all of them are real numbers. And we call that the linear system Ax equals b has one or more solution if b, the vector b, is in the column space of A. So this is the linear system. And we can rewrite it as, so notice that the first column are the coefficients of x1, second column are the coefficients of x2. So we can express in this form. Now you can see b, the vector b, is the linear combinations of the column vectors of A. Okay, so this is a linear combination of column of A. So that's why B is in the vector column space of A. Remember, column space is the set generated by the columns of A. Okay. So if the columns of A are linearly independent, then how many column vectors are there? We have n column vectors. That corresponds to the number of unknown, right? So if those n vectors are linearly independent, then they form a basis for Rn. Do you remember what is a basis? A basis, it can generate the entire vector space. So the basis has, in this case, has n vectors and they are linearly independent. Any vector in the vector space Rn is a linear combinations of the vectors in the basis. Okay, so now you can see any vector b can be written as a linear combinations of the basis vectors with the unique x1, x2, and xn. Okay, so if the columns are dependent, then they describe a subspace of Rn. So it's not the entire Rn, it's going to be a subspace. Okay, a linear subspace. So what is subspace and how do we find it? So therefore, in order to have like the system Ax equals to b have a solution, then b must be in that subspace, the column space. Okay, so what is definition of vector space? So it must satisfy the following properties. First, closed under addition. It means if u and v are in the set V, then u plus v, this new vector, is also in the set V. So this is closed under addition. So when we add them, this guy is also in the set V. Okay, next, closed under scalar multiplication. So if u is in V, then cu is also in V for any real number c. Okay, what does that mean? So it means, okay, let's say this is V. If V is in, u. This is u. If u is in the set V, then cu. So cu, if c is positive, then we're going to have this new vector in the same directions. If c is negative, then we have the new vector in the opposite directions. So these vectors must be in V, okay, the set V. It means the V contains this whole line, okay, with the directions of u. And what is the first one? Closed under additions means. So if two vector u and v are in the set V, well, it means the whole plane generated by this two vector u plus v must be in V, the set V. Okay, And then the next one contains the 0 vector. Well, it means the 0, the origin must be in the set V. Okay, so 0 vector is in V. Okay. Next, addition is commutative and associative. So A plus V equals V plus U. U plus V equals V plus U. So addition is commutative. Associative means we have 3 vectors. We can add the first 2 first and then add the third one, or we can add the last 2 first and then add the first one. So this is associative. And then there is an additive inverse minus U, which is minus 1 times U, such that U plus minus U equals 0. Okay, for all the vectors, there must be an additive inverse. Multiplication by scalar is distributive and associative. So when we multiply a vector by a scalar, we can distribute the scalar, and also if we have like the sum of the scalar multiplied by the vector, we should be able to distribute it. And if we have 2 scalar multiplied and then times U, is the same as we can multiply B times U and then multiply by A on the left. Okay, associative. Next, the non-empty set is a subspace of V provided V0 satisfies the same conditions. Okay, so the non-empty set V0 is a subspace of V. Then, first of all, it must be a subset. So this is subset. Okay, what does subset means? Okay, so when we talk about set, we talk about the relations. Okay, so A is in a set. This means A is an element of the set A. So for example, 1 is in the set 1, 2, 3. Okay, and then for the relation between 2 sets, we say B is a subset of A. It means all the elements in B are also in A. So for example, 1, 2 is a subset of 1, 2, 3. Okay, so this notation belongs to is for elements and sets, and then this notation is a subset. Okay, so and how do you write this guy looks like you put the horizontal line in the middle of the C, right? And then this guy looks like you have a C and then you put a vertical line on horizontal line under it. Okay, all right, so and because V0 is a subset of V, so that's why the operations of vectors in the capital V and will stay the same in the subset. So we just need to verify the following 3 conditions. First, conditions for subspace W. So we don't have to check all of this because we already have the operations in the bigger sets, so we already know how vector add or multiply. Okay, so now we just need the following 3 conditions. So W is the subspace of V. First, W is a non-empty subset of V. Second, close under addition. If U and V are in W, then U plus V is also in W. So close under addition. 3. Close under scalar multiplication. If U is in V, then CU is also in V for any real number C. Okay, and usually when we want to check W is a non-empty subset of V, we want to check whether the 0 vector is in W. Okay, because this is always the case. In order to make W to be a subspace, 0 vector must be in W. Okay, why is that? Oh, you can think of that is because of the this property close under scalar multiplication, we can let the scalar c be 0, then 0 times whatever vector is the 0 vector, then it has to be in W, okay, to satisfy this condition. Alright, next. Let's remember why we care. So the linear system has one or more solutions if B, the vector B, is in the column space of A, and the column space is a vector subspace of Rn. Okay, so column space is like an example of subspace. Okay, so let's look at example 1. Consider the set of vectors U such that A times U1 plus B times U2 plus C times U3 equals 0, where now A, B, C are given real numbers. For example, A is -2, B is 3, and C is 4. Okay, this is an example. For any given A, B, C real numbers, what is this guy? Okay, so this is in R3, right? So this is in R3. Then we know this linear equation in R3 represents a plane. And because the right-hand side is 0, so we know this plane passed through the origin. Why is that? Well, you can plug in the 0 vector. So when U1, U2, U3 are 0, you just get 0 equals 0. So because that vector is a solution of this plane, so this plane passed through the origin. Okay? Now we want to show this is a subspace of R3. So to show it is a subspace, we need to show it satisfies all these 3 conditions. Okay? So to prove it is a subspace, we want to check it satisfies all 3 conditions. So this is the proof. First, it's non-empty. Okay, so first we want to check non-emptiness. Well, we can check 0 vector, because for 0 vector we just plug in U1 is 0, U2 is 0, U3 is 0, and we get 0, check. So 0 vector is in so let W, let's call it W, to be the set of vectors such as blah, blah, blah. Okay, so let this be W. So 0 is in W, so W is non-empty. Next, we want to check close under addition. Okay, so what does that mean? We want to suppose we have like a U and V is in W, and we want to show whether U plus V is in W. Okay, what does that mean by saying U is in W? Let's say U is like U1, U2, U3. V is V1, V2, V3. They are in W, means U satisfy that A times U1 plus B times U2 plus C times U3 equals 0. And because V is in W, so it means A V1 plus B V2 plus C V3 equals 0. Okay, now we want to ask whether U plus V is in W. But what is U plus V? Well, when we add 2 vectors, we just add the entries respectively. Okay, and to say whether these guys are in W, well, it's the same as saying we want to ask whether A times U1 plus V1. So this is the same as saying we want to check whether A times U1 plus V1 plus B times U2 plus V2 plus C times U3 plus v3, this guy, is that equal to 0? And it is because we can add equation 1 and 2. So 1 plus 2, we get a u1 plus a v1, bu2 plus bv2, cu3 plus cv3 equal to 0. And when we factor out the a, and this is exactly what we want. So now we have check. Okay, so that's why u plus v is in W. So then we have close under addition. Next, close under scalar multiplication. Okay, what does that mean? So suppose u in W, and we want to show whether c times u is in W, where c is any real numbers. So u in W means u1, u2, u3. This vector is in W. So now we have this vector satisfy a u1 plus b u2 plus c u3 equal to 0, right? And then we want to multiply by c. Okay, so when we multiply by c, so c times this guy, it's like c times 0 is also 0, but what is this? Well, we can distribute the c, so c a u1 plus c b u2 plus c, oops, abuse of notation, so let's don't call this c, let's call it k. KCU3 is 0. Now, because this multiplication of numbers is commutative, so we can get a ku1 plus b ku2 plus c ku3 equal to 0. Well, this is the same as saying ku1, ku2, ku3 is in W, and this is exactly ku. So now we have shown that W, okay, satisfy the three conditions, is non-empty, is closed under addition, and is closed under scalar multiplication. So definitions of subspace, okay, and W is subspace of R3. So far, so good? Alright, let's continue. Now consider a plane that does not go through the origin. For example, u such that u1 plus u2 plus u3 is 2. Is this plane a subspace of R3? Okay, so here, to show W is subspace, we must prove it satisfies all three conditions. Okay, so first, non-empty. Second, closed under addition. And closed under scalar multiplication. Okay, and to show W is not a subspace, what we need to do is just find one counterexample, which violates one of the rule above. Okay? So now, in order to show this guy is not a subspace, let's find some example, okay? We can find, let's see. And we can, usually it's easy to check whether the zero vector works. So for the zero vector, okay, so consider the zero vector. Zero vector is 0, 0, 0. And then when we plug in 0 plus 0 plus 0, this is 0, which is not 2. So let's say W is the set of all U such that U1 plus U2 plus U3 equals to 2. Or maybe it's better to write like this. So it's a set U such that, okay, you can also put like this. Alright, and so now you can see 0 is not in W. This is a problem because it violates. Which rule it violates? Does it violate non-emptiness? No. We just show one vector is not in W, so maybe some other vector is in W. So it's not violating non-emptiness, but it is violate the clause under scalar multiplication. Okay, because we can pick a vector in W. Let's pick a vector in W. We can let U1 be 2, and then U2, U3 be 0. Then this guy is in W, right? And we let the scalar multiple to be 0. Now you can see 0 times, let's say this is called U. This is a 0 vector, and you can see 0 vector is not in W. So now we can show it violates the law of clause under scalar multiplication. And then you are done, right? So once you find a counterexample and then to show it violates one of the rules, you're done. Okay, but I want to show you another example, okay? So we can also try to show it violates the law of clause under addition. So we can consider, so 2, 0, 0 is one vector, right? We can say this is U. 2, 0, 0 is in W. And let's do one more. How about 1, 1, 0? You can try different vectors. 1, 1, 0 or 1, 0, 1, 1, 0, 0, 2. Does not matter. Lots of vectors you can show. Okay, this is also in W. But then what is U plus V? U plus V is, oops, sorry, press. Okay. Alright, so U plus V is 3, 1, 0. So 3, 1, 0, is this in W? Okay, now let's check. When we add those coordinates together, we get 4, which is not 2. So now we know this guy is not in W. So that's why we find two vectors in W, but their sum is not in W. So it violates the law of clause under addition. Okay, so right. So to show this problem, the W is not a subspace, you can just do either this guy or this guy. You don't have to do both. Okay, you just need to find one counterexample to show it violates one of the law. Okay, so far so good, everyone. Let's continue. Conclusion. A plane through the origin is a subspace. Yes. And a plane not through the origin is not a subspace of R3. Okay. Let's look at example 2. Consider all xy such that x times y times z is 1. Is this a subspace of R3? Well, let's think about what this means. Well, x times y times z is 1. First of all, we want to check whether the 0 vector is in it. And what happened? Okay, so please pause the video here and then think about it. All right, and have you finished? Okay, let's continue. Consider the zero vector. Zero vector, all the coordinates are zeros. And you see 0 times 0 times 0 is 0, which is not 1. Because the zero vector is not in W, then we know it is not a subspace. Okay, so W is the set of x, y, z such that x, y, z equals 1. Okay, and similarly, we can pick a vector. One vector is in W, so the 1, 1, 1 is in W, and then we have 0. So let k be 0. This is u. Now we have k times u is the 0 vector, which is not in W. So we have violate the law of close under scalar multiplication. So then we're done. So W is not a subspace of R3. Okay, then we're done. If you want to show another counterexample, yes, you can do it. You can consider U is 1, 1, 1. V is also 1, 1, 1. Then you can see U plus V is 2, 2, 2. So 1, 1, 1 is in W, right? But 2, 2, 2 is not in W because 2 times 2 times 2 is 8, which is not 1. So that's why you can see it also violates the law of close under addition. Now you can also see that so W is not a subspace of R3. Okay, so we have two counterexamples, and you keep in mind you only need to show one counterexample. And here I just want to show you more, so I show two. Okay, but you can pick other vectors, so you only need to show one counterexample. Okay, very good. Let's continue. Now let's generalize some concepts from R3 to Rn. So we call linearly dependent and independent vector. So here we have k vectors. So let's say k vectors u1, u2, uk. This is a typo. In Rn are linearly dependent if we set up this equation c1 u1 plus c2 u2 plus ck uk equals 0, and we want to solve for c1 c2 ck. So if c1 c2 ck and one of them is not 0, then we have those vectors are linearly dependent. But if all of them are zeros, then it means this equation is just like 0 vector equals 0 vector. It tells us nothing, so no relationship among those vectors. So that's why they are linearly independent. Okay, so the idea is very similar. We just extend the dimensions. So now notice that we generalize in two ways. First, vectors of length n. Okay, not only R3 is Rn, so vectors of length n. And k vectors, so k might not be n. Okay, maybe not only 3 vectors. In R3, it could be like 2 vectors in R3 or 1 vectors in R3. Okay. Not 1 vector, because 1 vector is only 1 vector. We at least need 2 vectors, then we can talk about the relationship among them, whether they are linearly independent or dependent. Okay. So the algebra is very similar. So first we want to set up this equation, and then this guy actually gives us a linear system, right? And then we have the u's on the column vector of this matrix A, and C is like the we want to solve for C, so this is like the solution X. And then the right hand side is the 0 vector. Okay, And we can use Gaussian elimination to find the C's, even if A is not a square. So it does not need to be a square matrix, but if it is a square matrix, we can compute the determinants. So determinants only works for square matrix. Determinants only define for square matrix. So if A is not a square matrix, then you just do the Gaussian elimination to solve for the C's. Okay? And when it is a square matrix, we compute the determinants. If the determinant is not 0, then we have a unique solution, which is the trivial solution. So all Ci's equals 0. So that's why the vectors are linearly independent. And then if the determinant is 0, it means we have infinite many solutions. And it means that there is some Ci which is not 0, so that's why we get linearly dependent. I'm going to fix this handout. Okay, we get linearly dependent for the UIs. Okay, good. Let's continue. Example 3. We have U1 and U2. Are these vectors linearly dependent or independent? So we have two vectors in R4. Right? So we want to set up, okay, A U1 plus B U2 equals 0. We want to solve for AB. Well, this is the same as solving the augmented coefficient matrix U1, U2, and 0. So U1 is 1, 1, 0, 1. U2 0, 2 minus 1 0, and then right hand side is zeros. Okay, now let's see. First thing, we make this guy 1. Oh, and it is 1, and then we can use it to cue the entries below it, right? Okay, we can do minus R1 add to R2, and the good thing is because this is zeros, so it won't change the second column or third column. Just the first column, they become zeros. So here minus R1 add to R4 as well. Okay, next we want to make this entry 1, so we can do 1/2 R2. And then we can use it to cue the entries below it. So R2 add to R3. Alright, now can you see we have echelon form? So we can stop here and then we can look at the first column, the coefficients of A. Second column corresponds to the coefficient of B, and the third column is the right hand side. Last row tells us that, second row. Okay, second row tells us that 1 times B equals 0. First row tells us that 1 times A equals 0. Oh, we get both A and B are 0. It means when we plug into this equation, we just get 0 equal to 0. It tells us nothing, so no relationship among those two vectors, then they are linearly independent. So U1, U2 are linearly independent. Okay, so far so good, everyone. Alright, let's continue. Oh, okay, what if we have k vectors in Rn with k greater than n? Okay, let's think about it. Let's say we have 3 vectors in R2. What do you say? 3 vectors in R2 must be linearly dependent. Because R2 has dimension 2, right? So it means the basis only contains 2 vectors. So if you have 3 vectors, then one of the vectors must be a linear combination of the other 2 vectors. So that's why, similarly here, if k is bigger than n, then there must be some vectors is a linear combinations of the other vectors. Okay, so can they be independent? No, they are dependent. So far, so good, everyone. Maybe let me write down. So n is the dimension of n. Okay, so the basics must have n vectors. So that's why if you have more vectors than n, then well, some of them must be linear combinations of the other vectors. Okay, very good. Example 4. So consider 3 vectors in R2. Are these vectors linearly dependent or independent? To make the problem more interesting, I changed the numbers. Okay, so now we have U1, U2, U3. So we have 3 vectors in R2, then we know they must be linearly dependent. Okay, so what we want to do is we want to write a linear equation involving these 3 vectors. Okay, what we do is we want to set up the equation. So A U1 plus B U2 plus C U3 equals 0. And we want to find out what is ABC, right? Okay, it corresponds to the augmented coefficient matrix U1, U2, U3, and the 0 vectors. So this guy equals 4, 1, 1, negative 3, and minus 10, 5. Okay. So now let's see. Okay, what we want to do is first we want to make this entry 1. Okay, so let's swap row 1 and row 2. And we have 1 minus 3, 5, 4, 1 minus 10. Then we have use the one entry to Q the entry below it. So minus 4 R1 add to R2. 1 negative 3, 5, 4 minus 4, 0. 1 minus 4 times negative 3, so 1 plus 12, which is 13. Minus 10 minus 4 times 5. So minus 10 minus 20 is minus 30. Okay, good. Now we're in the echelon form. So the first row, oh, I almost forgot. There are the 0 vector on the right hand side, right? Okay, so now first row corresponds to the coefficient of A, B, C, and right hand side. Okay, so the last row, oh, now can you see what happened? Here we have a leading coefficient, here we have leading coefficient, but this column has no leading coefficients. It means C is free. So C is free, we have infinite many solutions. Good, because we know these vectors are linearly dependent. Of course, we want to have infinite many solutions. Okay, we don't want a unit solution, right? Okay, C is free, so let's see BT. And then the last row tells us that 13B minus 30C equals 0. So B is 30 over 13. But C is T. Okay, and then the first row tells us that A minus 3B plus 5C equals 0. So A is 3B minus 5C. 3B, 90 over 13T minus 5C, so 5T. Okay. let's see. 5 times 13, 65. So 90 minus 65, is it 25? Okay, 25 over 13c. Okay, good. Now, oh, c is t, so we just replace c by t. Okay, and this is t as well. Okay, now we can plug in. We get 25 over 13t u1 plus b is 30 over 13t u2, c is t u3 equal to 0. And in order to make them look nicer, we can pick c to be 13, then it will clear all the denominator. So this is the equations involving those 3 vectors. And then we finish this problem. Okay, so far so good, everyone. Alright, so we're gonna continue in the next video. See you soon!